Hi, everyone. I'm very excited to be here. Thank you for inviting me to give this presentation today. I'm going to talk about I pressed the wrong button. How do I?
This one moves you forward, the green.
Okay.
And if you want to go back to red one.
Perfect. So the work that we do at JP Morgan in the area of quantum. As you can see here, we actually built a fully fledged research lab. It's called the Global Technology Applied Research. I'm the head of this great team. We do traditional research in areas that are maybe kind of intuitive when it comes to a bank, for example, cloud computing or blockchain, but we also do research in areas that are really like cutting-edge technology, particularly quantum computing and quantum networks and security. So today I'm going to talk about these two areas. Yesterday there was a workshop on security. Dr. Charles Lim, who is the head of the quantum communications and security effort, presented there. But I'm going to give you a quick overview as well. So just to give you an idea, like a lot of people sometimes are skeptical about a bank doing research. It's really like a true research because we have a very large team of PhDs, some software engineers and network engineers as well. We publish our results aggressively. Every single thing that we do, we publish on archive, journals, and conferences. Since the inception of this research lab almost 5 years ago, we have been able to publish over 100 scholarly articles that have collected over 2,000 citations from the scientific community in very prestigious venues like Nature, Quantum, NPJ Quantum Information, Nature Physics, and so on. So the reason why I'm saying all of this is to demystify the misconception that banks don't do research in technology. We actually do, and we are very serious about it, particularly about quantum. As a matter of fact, we have a very large team, and we also made an investment in Quantinuum, a significant investment in December of last year, so this shows how serious we are. And we're also hiring aggressively, so in case anybody's interested, that's what we're doing right now. So basically, if you look at this diagram here, you can see from left to right, we are exploring different ways to do optimization. And the reason why I'm focusing on optimization here is not because this is the only thing we do. We do much more than that. We do also, say, Monte Carlo integration. We do machine learning. You will see something around these areas as well today. But definitely optimization is a big use case, a big domain in finance. A lot of financial use cases all boil down to optimization algorithms. So we go from analog to digital, so from adiabatic algorithms to fault-tolerant quantum computing algorithms, which will be used in the future. However, we're already defining them. So in the area of adiabatic quantum optimization, we worked, for example, with AWS. We published a paper in Physical Review Research showing how an adiabatic algorithm running on a neutral atom quantum computer can solve an optimization problem, such as portfolio optimization. Moving to the right, in the area of digital, we actually defined an algorithm that is kind of a meta-algorithm in the sense that it takes any branch and bound solver, classically implemented, for example, in traditional solvers such as Gurobi and Cplex. No matter what heuristic has been included in that particular solver, we can achieve a quadratic speedup using our quantum meta algorithm. So it's kind of a universal quadratic speedup. So in the middle, we have something that stays between analog and digital, so something like analog-inspired digital solutions. And so we focus a lot on QAOA, the algorithm that I think JP Morgan Chase has become very strong in. It's almost like we became a powerhouse on this algorithm. And so I'm going to talk about some of the results here. The one on the left, for example, is a demonstration of scaling advantage, which is different from quantum advantage or quantum supremacy. It means that we understood that there is actually a trend towards quantum advantage. we were not able to prove quantum advantage yet in this particular case because we needed more qubits, but the trend is there, which is very promising. This has been published in Science Advances. And then we worked also with Quantinuum and Argonne National Lab on a new solution for random circuit sampling. And this again will be presented in a moment. So let's talk about the scaling advantage solution. So we wanted to take an optimization problem that actually explodes quickly, explodes fast, in the sense that many optimization problems with exponential complexity explode as the size of the problem becomes bigger. However, we didn't want to have a size of like thousands. We wanted to see a problem that exposes this explosion characteristic as soon as possible. So these low autocorrelation binary sequences labs, this problem that is actually very important in math, physics, engineering, as well as finance, is a problem that explodes to the point that it is classically intractable at n equals 67. We took this problem. As you can see, like there is a mathematical formulation here. The whole idea is to compute the lowest possible energy with certain constraints. And we were able to demonstrate numerically and empirically that the complexity of QAOA with the quantum minimum finding technique offers quadratic speedup compared to Gurobi and Cplex, which are the traditional solvers in classical computing. In fact, if you take the complexity of Gurobi and Cplex and you do the square root of that, you can see that you get 1.21 to the power of n. So how is this a proof of scaling advantage? Well, we actually saw that with 40 qubits simulated by our simulator, which became actually an open source project. It's a very aggressive simulator. I recommend that you guys maybe download it. It's called the QO kit, Quantum Optimization Kit. So this particular simulator with 40 qubits and demonstrated that the trend is there. So up to 32 qubits, the number of qubits that we had from Quantinuum, we used the hardware. From 32 to 40, we used the simulator, and we demonstrated that the trend remains consistent, which is a promising result, making us believe that as we reach n equals 66 or 67, as you can see here, we will be able to prove the quantum advantage result that we need. But now going into the field of random circuit sampling, you probably remember the paper by Google published in 2019. They also followed up with another paper in 2023, and USCC in China had another paper in 2021. So the focus was on random circuit sampling, and originally was claimed as a quantum supremacy result. Then there were some claims stating that the same result could have been achieved classically. We re-implemented it completely using the Quantinuum quantum computer with 56 qubits, the current one with very high fidelity, all-to-all connectivity, and we were able to demonstrate random circuit sampling in a way that it is billions of times above the classical counterpart. And when it comes to energy consumption, we're talking about 30,000 times less energy consuming than its corresponding classical part. So this is an example of an algorithm running on a real hardware, solving a problem that most likely is intractable using classical computing. And it's very exciting that we have been able to achieve this result with both Quantinuum and Argonne National Lab. So the other problems that I wanted to touch upon is about machine learning. So retraining problems, retraining models is actually a very prohibitive task. And so what happens is that many algorithms for machine learning use variational algorithms, which are exposed to limitations. So people observed that there are limitations in these algorithms, consisting of something called the barren plateau. So there was a conjecture postulated by Los Alamos National Lab, conjecturing that the decay of the gradient is actually directly dependent on the dimension of the corresponding Lie algebra. So we proved this conjecture, and so we were able to actually identify when this problem arises and when it can be avoided. So based on this solution now, researchers have an opportunity to decide whether or not variational algorithms should be used. So it's an important result because it can actually guide in the choice of the solution for variational algorithms when it comes to retraining machine learning models. Another important problem that we actually saw in finance is, of course, fraud detection, anomaly detection in payments. For example, when payments are processed, they have to be processed in a matter of like 5 seconds. And a lot of scrutiny is around payments because sanction entities have to be avoided. So it's necessary to quickly execute this these use cases without incurring into false positives or false negatives. Retraining these models is also very difficult, just like I mentioned in the previous slide. The majority of these algorithms are based on decision trees. The complexity, classically, of decision trees is linear, which doesn't sound so bad, at least it's not exponential. But the problem is that the dimension of these vectors is in the order of billions. So even a linear complexity, when you have a billion or even more dimension of the vector space, becomes prohibitive. And that's why we have false positives and false negatives, because we have to basically use approximations. However, with our quantum algorithm called DESQ, we were able to achieve logarithmic complexity. And when you go from linear to logarithmic, you actually have exponential speed up. So a very exciting result, which reduced the complexity dramatically, making the problem scale much better. Of course, when I say that the problem scales much better, I just want to emphasize this is not yet usable in production. It's still an algorithm that we implemented, hoping to be able to use it in the near future, or maybe mid-term, long-term, but as long as quantum computers support this type of complexity. And finally, still in the area of quantum computing, I wanted to mention a problem in the area of federated learning, very important in finance, especially when you do computing, machine learning at the edge. So the problem is that these computations are very efficient. There is no doubt about it. That's why we do federated learning. But the communication between clients and servers can be an exposure of confidential data. And using homomorphic encryption, which is the solution that has been implemented so far, is good up to a point, because homomorphic encryption performs very slowly. And when you do homomorphic encryption, you encrypt the data with your public key before sending it out. So technically, your data is secure, because the only entity that can decrypt the data is yourself with your private key. So you ship the data out, encrypt it with your public key, but in order for the server to be able to operate homomorphically on that encrypted data, you have to ship your public key as well, which is an exposure given, as we heard in the previous presentation, public keys are an exposure to quantum computing attacks, because attackers can use the public key to reverse engineer the corresponding private key using Shor's algorithm. Or maybe, who knows, post-quantum cryptography algorithms may be vulnerable in the future as well. There is no guarantee that they will not. So for this reason, we implemented a communication strategy based on quantum communications, and we solved the problem efficiently. So this actually leads me to the next and final topic, which is security. So since I just mentioned quantum communications, we have a very solid team at JP Morgan Chase of PhDs, researchers, and network engineers working on in the area of quantum communications, and particularly quantum cryptography. We have a dual remediation strategy at JP Morgan Chase. We believe that Doing just post-quantum cryptography is not sufficient for the reasons I mentioned before. There is no guarantee that post-quantum cryptography algorithms will have everlasting security. We have actually here in this conference a booth I would recommend you guys visit, hosted by the creators of quantum key distribution. It's a technology that was created by IBM 40 years ago, 1984, by Gilles Brassard and Charles Bennett. They have a booth here called the BB84, because it's exactly the two initials of the researchers, and 84 is the year. So that's what we are doing at JP Morgan. We believe that we have to work in parallel on rolling out both post-quantum cryptography and the quantum key distribution. Quantum key distribution has the advantage of transmitting the key with provable security. In other words, every eavesdropper attack will be detected by both Alice and Bob, the two parties communicating with each other. So when the key is exchanged and established between the two parties, the presence of an eavesdropper will be automatically detected, which is a property that we have never seen in classical cryptography. So that's why we are excited to say that at JP Morgan Chase we're pursuing both approaches, post-quantum cryptography and the quantum key distribution, where PQC is mostly used at the application layer and QKD is delegated to work at the network layer and encrypting everything underneath. So this is the end of my presentation, and thank you very much for attending. And before I conclude, this is the barcode, the QR code, in case you guys have friends or yourselves are interested in joining JP Morgan Chase. We're hiring aggressively in both QKD and quantum computing. And there is so much going on at this point. If you compare what happened at the Quantum World Congress 2 years ago when I presented the first time here, last year again, and this year, you see the incredible progress that has been done in this technology at every level. So even our team was kind of small maybe 2 years ago, and it's now very large, and we have an investment in Quantinuum and so on. So let other people know that we are very much interested in hiring talent right now. Thank you again.